Let's consider this thing. F of z is equal to 1 over z minus 1. And when we find the Laurent expansion, so from now on, Laurent expansion is L expansion, or L series, in the following domains. So A, this domain, just the punctured ball around 1, around 0 of radius 1. B is the set of z such that mod z is bigger than 1. C is the punctured, let me just write it. It's the set of z such that z minus 1 is like this, and then D is the set of z such that mod z minus 1 is bigger than 1. That is our question. And notice these are all different annuli. So we have this function that has a singularity at 0 and has a singularity at 1, right? And this thing here, the ball of radius 1 around 0, is this annulus like this, that just avoids 0, right? And sure enough, this annulus fits inside the domain omega where this thing is holomorphic. Yeah, so we can indeed apply this theorem, and there should be a Laurent expansion in this punctured ball, right? So this is A. Yeah. Give me a thumbs up if you're with me here. Cool. All right. What's the domain B? B is everything outside the ball of radius 1, right? Which is another annulus. It's an annulus which has got infinite radius on the other end, right? Yeah. So that's A, and then B is everything outside. So I don't know how to really draw that well. So that's B is everything outside here. So that's B. All right. So maybe I should point out A is the interior, not the circle itself. So this is A itself, yeah, but not this thing. This is a punctured ball. B is everything outside. Let's think about this thing. This is the annulus of radii 0, 1 around 1, right? So what annulus is this? So it's got this inner radius of 0 around 1 and this outer radius of 1 like this. Yeah? That's what C is. So C is this thing right here. And sure enough, it's another annulus which is inside the domain on which F is holomorphic. So this is also true. This is another annulus inside our domain where we have a unique Laurent series. The Laurent series, as you saw from the proof, was completely defined by its coefficients, which are defined by whatever closed curve we integrate around these coefficient expressions on, right? Yeah, so it's entirely uniquely defined on whatever annulus we decide to do the expansion on. Yeah? And then the final domain D is everything of radius bigger than 1 centered on 1. So that's everything outside here. You get another color. So D is everything outside here. And again, it's an annulus where the thing is holomorphic, right? So we have these 4 different annuli here where we're going to calculate the Laurent series of the same expression, of the same function. Yeah? Cool. Yeah? So we should expect to have 4 different Laurent series a priori, right? Yeah, it's the same function, but since the expansion holds true in 4 different domains, we expect different coefficients in each case. Yeah? Could be some fluke and we don't get different coefficients, I guess, but generally would expect different coefficients. Okay, so what's our function? Our function is f of z is equal to 1 over z minus 1, right? And let's do our first domain A, which was the punctured ball of radius 1 around 0. Yeah? So look at this thing here. So obviously we're not going to just start to compute the coefficients of the Laurent series. That'll be a lot of work. We don't want to do it. We want to come up with the series, right, somehow, because once we come up with the series, then then that has to be the series because the series is unique in this annulus. So A in this thing. Okay, so if we're expanding in this thing here, yeah, what do you see happening? How can we come up with a series in this punctured ball? So recall, I mean, once again, any series you come up with which is valid inside this punctured ball is the right series by uniqueness. So you have the right to do anything you want, so long as you come up with a series which holds true inside the punctured ball. So typically, if you saw this in calculus, what would you be looking for? Right, we'd look, right. Yeah, typically in calculus, if you're asked to come up with some Taylor series without coming up with the coefficients, you're going to use some trick which involves using geometric series, right? Yeah. Either some algebra to turn it into something like 1 over 1 minus whatever, right? Or you're going to differentiate it to turn it into something which after algebra goes into 1 over 1 minus, or integrate it to turn it into something which after algebra goes 1 over 1 minus whatever. So we're going to use the same thing here, right? So we're going to write this like this and then like this. Yeah? And then we're going to write this as minus 1 over z, 1 over 1 minus z. Yeah? And now we're happy because we see what this is, right? This is this geometric series like this, and that's cool because now this is the sum from k equals 0 to infinity of minus z to the k minus 1, right? And then we can instead take this sum from k equals minus 1 to infinity minus z to the k, like this. And then this is exactly the Laurent expansion, right? Yeah. So the first term is minus 1 over z. The next term is minus 1. The next term is minus z. The next term is z minus z squared, and then minus z to the 3, and so on. Yeah. And this converges for any z inside this punctured ball. So it makes sense and converges inside this punctured ball, and that's it. So it has to be the Laurent series. And the first non-zero term is this 1 over z, which makes sense because you look at this and you see that you have a pole of order 1 at 0. So that should be the first non-zero term. Yeah? Cool. So by uniqueness, uniqueness, this is the L series. All right, cool. Let's do B. So B was everything outside the ball of radius. Ball of radius 1 around 0. So we can write this as 0, 1, infinity. And write this as a sentence. So inside for z in A of 0, 1, infinity, i.e. everything outside the ball of radius 1, strictly inside. So everything outside the closed ball of radius 1 around 0. So here we're going to again apply some trickery, right? Because we don't want to actually calculate coefficients. Yeah? Okay, but if we apply some trickery, then that means we're going to have to expand something using geometric series. Yeah? But now we can't expand it in terms of z because mod z is bigger than 1, right? Yeah. So what would we expect to expand things in terms of, given that we have to make it converge here? 1 over z, right? 1 over z, because if we have 1 over z, then 1 over z is absolute value less than 1. So we have the hope that the geometric series will converge for 1 over c. Yeah. So need the geometric series to converge so has to be the geoseries in 1 over z. Yeah, cool. So we somehow have to come up with some algebra to turn this into something like 1 over 1 minus z. Yeah, but that's not hard to do, right? Because f of z equals 1 over z, z minus 1, and let's write that as 1 over z squared 1 minus 1 over z. Cool. Yep. And then we write this as 1 over z squared, and then 1 over 1 minus 1 over z. And this thing is indeed something we now can expand with the geometric series. So then it's the sum from k equals 0 to infinity of 1 over z to the k, which is the sum from, whoops, which is 1 over this thing, the sum from k equals 0 to infinity of z to the minus k, like this. And then this is the sum from k equals 0 to infinity of z to the minus k. So yeah, we are starting therefore at minus 2. We are starting at minus 2. There we go. So then the first term is z to the minus 2 plus z to the minus 3 and so on like this. C, which was the punctured ball of radius 1 around 1, right? So inside, oops. Okay, so what are we going to be expanding? So again, we're going to have to try and get the geometric series in action again, right? What are we going to expand inside the geometric series? Given that this is what we have. C minus 1, indeed. Because z minus 1 is the only thing in play which is going to have absolute value less than 1, right? Yeah? And of course, we're always expanding around the singularity. So it has to be z minus 1. Yeah? It has to be z minus 1. So we have to do some algebra to turn this into this thing. Into this thing. F of z is equal to this. And what is this? Let's write this like this. Z minus 1, z plus 1 like this, and then z minus 1 like this, right? And then let's write this thing as 1 over z minus 1. And what do we have here? Let's write this guy as 1 minus this thing, right? So then this is 1 minus, or we don't have to do it. Let's do it that way. Z minus z minus 1. Like this. Yeah? So then we have z minus 1, and then this thing is just the sum from k is equal to 0 to infinity of minus 1 to the k of z minus 1 to the k, and then this is the sum from k is equal to 0 to infinity of minus 1 to the k of z minus 1. Oops. To the k minus 1, and the first non-zero term is, the lowest negative index is minus 1, which is what you expect because you're doing a pole at minus 1. Cool. So this is Laurent series. So the first term is z minus 1 to the minus 1. When k equals 1, we just have minus 1. When k is, we have minus 1, yeah. When k is equal to 2, we have z minus 1. And when k equals 3, we have z minus 1 squared, and then so on, like this, yeah? Cool. All right, final domain is everything whose absolute value, start again, is mod z minus 1, absolute value bigger than 1, right? So it's the annulus around minus 1, 1 infinity. So as I raise the board, think about how we're going to do this. Again, we're going to use geometric series somehow. What are we going to use as the thing we expand inside the geometric series? We have to use either z or 1 over z, z minus 1 or 1 over z minus 1, given that we have a Laurent series which has positive and negative powers. So we need one of those four things to be expandable inside our domain, right? And in the domain, which is the annulus of centered around 1, which goes 1 infinity, then this thing oops. Or we need to use z minus 1 to the minus 1 as the geometric series. Because nothing else will converge, right? There's no other thing that has any chance to converge. So we have f of z, again, is 1 over z, z minus 1, like this. And we're going to write this as 1 over z minus 1 plus 1, and then 1 over z minus 1, like this, right? So this guy is going to leave alone. So this is the guy we are interested in. So let's write it like this. Z minus 1, and then 1 over, let's put it like this, 1 plus z minus 1. All right, what thing now would you like to do? What's your next algebraic move? Perfect, yep. So let's write that as z minus 1 squared, and then we're going to pull out a z minus 1 from this thing. So we're going to have 1 plus 1 over z minus 1, like this, yeah? And now we have something that we can actually expand with the power series. Yeah. Have we got the signs correct? Yes, we do. So let's write this as 1 over z minus 1 squared, and 1 over 1 minus 1 over z minus 1, like this. Yeah, like this. And then power series this thing. Minus 1 to the k, 1 over z minus 1 to the power k, like this. And what do we get from this? We're going to get sum from k is equal to 0 to infinity. And this will be minus 1 to the k, z minus 1 to the minus k minus 2. So that's the same as the sum from minus infinity up to minus 2. I have to be careful with the powers, but I'm okay because it's power 2, so it's like this, minus 1 to the k of z minus 1 to the k, like this. Yeah? Cool. Yeah. So that is the Laurent series expansion. So we're going to have z minus 1. So it's minus 2 and then minus 1, z minus 1 to the power 3, and then plus 1 over z minus 1 to the power 4, and so on and so on and so on. Yeah? Cool. All right, so that gives it, right? That gives us, so this is the L series. So we have that in each of these 4 different annuli where we can do a Laurent series expansion, we have different Laurent series coefficient, right? We have a different series depending on the annuli. Yeah.